5, we need to evaluate some more improper integrals. All right, you can see in number 4 we have infinite bounds on both sides, but we can still let a be infinity. If I can get an infinity symbol here. All right, so we would be looking at the limit as a approaches infinity, going from negative a to a, and we would have x e to the negative x dx. All right, so we can tackle it that way. It makes things a little bit easier. All right, now the antiderivative here is going to involve some integration by parts, so let's tackle that. So let's let u equal x and dv be e to the negative x dx. V is going to be equal to negative e to the x, negative e to the negative x, and du is going to be equal to dx. Alright, so uv minus the integral of v du. Alright, so negative x e to the negative x minus the integral of v du is going to be negative e to the negative x dx. Those two negatives will make a positive. When I integrate, right, now this is over the interval of negative a to a, but we'll cross that bridge in a sec. We're going to just kind of lump that all in at the end. All right. So we'll have negative x e to the negative x. The antiderivative of e to the negative x is negative e to the negative x, and we're going to evaluate that over the interval of negative a to a. All right. So everywhere I have an x, replace it with an a. Everywhere I have an x, replace it with a negative a. So negative a e to the negative a minus e to the negative a minus negative a e to the negative a minus e to the negative a. Alright, so we got a lot of double negatives here, so let's try to keep this in order here. So negative a e to the negative a minus e to the negative a minus a e to the a minus, two negatives make a positive, e to the a. Alright, does not look like we have any like terms that could be simplified, so I'll apply my limit as a approaches infinity. All of this, I mean, we can factor out some GCF, and I can pull out at e to the a, e to the negative a first, and that would be a negative a minus 1, and then I could pull out an e to the a, and that would be a negative a plus 1. Doesn't look very helpful though. Alright, so when we go to plug in infinity, we have some good things and we have some not so good things. Alright, so if we have e to the negative x, so e to the negative x, that's going to go to 0 just by the nature of the exponential. Alright, so as we go out to infinity, we have a horizontal asymptote going to 0. So this whole thing zeroes out nicely. Alright, regardless of what happens inside the parentheses, the e to the negative a goes to 0. But what we're left with is the limit as a approaches infinity of e to the a times negative a plus 1. So we're looking at e to the infinitieth, right? Well, the end behavior of exponential e is infinite. So regardless of what's happening in here, we're looking at something that's not going to converge. So this one diverges. All right, because it's going to have an infinite result. So we're looking at infinity multiplied by negative infinity, so results some kind of negative infinity. All right, bottom line is we're not going to get something convergent. So looking at number 5, this one doesn't have any infinities in it. But if we look at it carefully, there is an asymptote at x equals 0. So we have to account for that. All right, so let's take a look at the actual graph. So 1 over x to the 1/3, but I'd just use the cube root function. Cube root of x, standard zoom, and you can see here that there is a break in the graph at 0. All right, so we have to account for that. And so what we'll do is we'll look at this as going from -8 to 0, 1 over the cube root of x dx, and then going from 0 to 1, same deal. All right, so now what we have to do is establish how this is going to work in terms of limits. All right, so we never want to actually get to 0. 0 is the bad number. So let's let a be 0. So we would be looking for, copy, paste, essentially the same set of integrals, just going from -8 to a and a to 1. All right, the act of finding the antiderivative should be easy enough, but we do need the limit as a approaches 0 now instead of infinity. All right, so we're going to rewrite. We're just focusing on the integrals at this point. So this is the same as saying x to the -1/3 power integrates to x to the 2/3, increase the exponent by 1, divide by the new exponent 3/2. And that's going to be over the interval of -8 to a. And then the same thing over the interval of a to 1. All right, so we're going to evaluate each of these, and then we'll get into the limit part of it. All right. So, I apologize for any noises in the background. So I'm going to pop in the the a first. 3 over 2 a to the 2/3 minus 3 over 2 -8 to the 2/3. And then we're going to have the same stuff just with 1s and a's. So plus, same stuff, just with a 1 and an a. Oops, a little heavy. So 1 and a. Alright, so we have 2 identical pieces here that can go away. So that's nice. Doesn't always play out that way. Alright, and in fact, the part of this that made it something that would be problematic is no longer in existence. All right, so we're in good shape here. So then it's just a matter of simplifying these. So this is the cube root of -8, which is -2, squared. So the cube root of -8, which is -2, squared is going to be 4. Times -3/2 is going to be -12 over 2, so -6. And then this one, well, 1 to any power is just 1, so plus 3/2 Probably should have left it as the 12 over 2. So we're looking at negative 9 halves. And now we can apply the limit. Kind of easy to forget that that's a thing. Limit as a approaches 0. Limit of a constant is equal to a constant, so this one converges, right, giving an area of negative 9 over 2. All right, so if we're going from negative 8 to negative 1, I'm sorry, negative 8 to positive 1, we're going to have more area that is negative than positive. So the positive pieces would cancel each other out. And so really you're only looking at negative 8 to negative 1, whatever that area is, and this process accounts for that. All right. So then the last one, same idea. If we get to an x value of 2, then we're undefined again. All right, so let's take a look at that picture. So alpha y equals x plus 1. Then we're going to have the square root of 4 minus x squared. Now I only care about 0 to 2, so I'm going to put that in my domain. Pretty good window. All right, so we're asymptotic at 2, so we have an asymptote at x equals 2. All right, so what we would do is find the limit, so we're going to let a be 2. As a approaches 2, going from 0 to a of x plus 1 over the square root of 4 minus x squared dx. All right, so at this point it's, all right, well, can you find the integral? Now, there's a couple of ways to handle this. One, you could use the separating the numerator technique. Another way is to just jump right into the trig substitution technique. All right, you see the 4 minus x squared on the bottom. You know, you could do a little mixing and matching of the two. All right, so if you see something in the form of a squared minus u squared, then right to a triangle. The a is equal to 2, the u is equal to x. If I want to manufacture that exponent there, I would want to have the x here and the 2 here, giving me 4 minus x squared as the missing side. All right. So then, and really this is just going to determine whether or not I want to split that fraction up. We'll see in a minute. So the sine of theta is equal to x over 2. The cosine of theta is equal to the square root of 4 minus x squared over 2, in which case the square root of 4 minus x squared becomes 2 cosine theta. X is equal to 2 sine theta. Dx is equal to 2 cosine theta d theta. Alright, so now I'm going to make my substitutions and see how this plays out. So the dx can be replaced. My x can be replaced. And my radical 4 minus x squared can be replaced. Alright, so I'm looking at the integral, and I'll get my limit and all that good stuff in there too. This should be a 0. I'm going to have the x, which is 2 sine theta, plus 1 over 2 cosine theta times the dx, which is 2 cosine theta d theta. So it actually is kind of clean because these are going to cancel out and give me something that's very easy to integrate. Alright, it doesn't always play out that way, but when it does, it's very nice. Alright, so I'm going to take care of this. Now, in terms of the bounds, the bounds really aren't a and 0. I never really should have had those to begin with. I should leave it boundless. And in fact, what I can do is leave the limit and the bounds off, because those apply to A, not to theta. Alright, so I'm going to hang on to these for later. I'll just put it over here. Yeah, you know what, I'll take this too. Just going to keep that safe for a few minutes. Oh, actually, now that I think about it, I'm not going to need the integral anymore, but it was a thought. The antiderivative of sine, negative cosine. So negative 2 cosine theta plus theta. Now, normally I'd say plus c, but we're working with a definite integral, just kind of in disguise. All right, so if I want theta, I keep doing that. I want theta, I'm going to take the inverse sine of both sides, so theta is going to be equal to the inverse sine of x over 2. Cosine, we already know cosine, adjacent over hypotenuse. Alright, so negative 2 multiplied by this is going to give me a negative, I'm going to find some room here, negative square root of 4 minus x squared plus the inverse sine of x over 2. Now that it's back in terms of x's, I can evaluate it over the appropriate interval, which is a to 0. All right, so, oh, I'm sorry, 0 to a. Justify the fact that I copied this. Alright, so if I replace all of my x's with a's, now I'm just going to get the same expression with a's instead of x's. Alright, so I'll make that substitution. Now if I replace all my x's with zeros, well, the inverse sine of 0 is 0, so that part's okay. But if I replace that first x with a 0, I'm going to get negative the square root of 4, which is going to be negative 2. Something that it's going to be a negative 2, giving me a positive 2. Alright, so, I mean, we could just kind of write that all in one shot. Alright, so we have to take care of everything else at this point. Now, we are approaching an a value of 2, so if I make my substitutions by applying the limit, we should end up with something that cleans up kind of nicely. Alright, so I'm plugging in a 2 everywhere I have an a. This is going to go to 0. If I replace this with a 2, the inverse sine, that goes to a 1, inverse sine of 1 is going to be equal to pi over 2, so we're looking at pi over 2 plus 2. So this one definitely converges also.